Welcome back to AP Physics C Mechanics. Today we are working on work, which you have learned before in the context of energy in some other class, I'm sure. But today we're going to expand those ideas into something that's a little bit more rigorous. All right, so typically in your introductory or high school physics classes, you see the typical work equals force times distance, and that's how many people define it. But that's not quite a precise definition. The precise definition, well, a more precise definition is work equals force dot distance, because force is actually vector, and counterintuitively to things that you've learned before, distance is also a vector. Probably in your kinematics class you heard vector or distance is a scalar, and in that context it kind of is. But this time around, the distance is like your distance along a certain specified path, and on that path you are going a direction. So for most introductory cases we use a straight line. Your distance is how far you travel along that straight line. But in general, that path can be, curved or whatever shape you want it to be, but it does have a direction along that path. So our distance here is actually a vector, and as such, when you do a multiplication of two vectors, you have to either do the cross product or the dot product. Work is defined as the dot product or scalar product of force and distance vectors. Now I'm using distance here because that's what is typically used. If you're looking in the textbook, it actually defines that as S. F dot S means the same thing. I'm going to keep using D for distance though. Now this definition only works exactly correctly when your force is constant. Constant force. This is the constant force definition. So it's kind of limited, but there are lots of constant force cases, so it is useful. The example I'm going to use for this case is from your textbook. It is actually one of the exercises, not one of the examples. It's going to be exercise 6.8. Let me pull it up real quick. Okay, so here it is. It says a loaded grocery cart is rolling across a parking lot in a strong wind. You apply a constant force of 30 newtons in the I direction or X direction and negative 40 newtons in the J direction to the cart as it undergoes a displacement of S, which we're using as D, equals negative 9 meters in the I direction minus 3 meters in the J direction. How much work does the force you apply do to the grocery cart? So our definition here is work equals force dot distance. Okay, so we can write these vectors. I'm going to be using like the bracket notation because I like it. It's 30 in the I direction and then negative 40 in the J direction. This is the I and this is the J. So you could include a K here of 0, which is basically going to be pointless because when you do the dot product it'll end up 0 times 0. If you want to include it, you're welcome to do so, but I'm not going to. And then for the displacement, we've got a negative 9 meters and negative 3 meters in the J direction. So now we get to do the dot product of those two vectors. When you do the dot product, you're just going to take the similar components and multiply them, i's together. 30 times negative 9 is negative 270, and negative 40 times negative 3 is positive 120. So when you add or subtract, whatever you want to call doing that, negative 270 plus 120, you're going to get negative 150 joules of work. Work is measured in joules because it's a transfer of energy, so it has the same unit as energy. But more on that next time. Now, this could also be accomplished if you did not have the exact components of your vectors, if instead you had magnitudes and directions. And that's where the other definition you'll sometimes see comes in. That's the F, D, cosine, theta. So really that is saying the magnitude of the force times the magnitude of the displacement times cosine of the theta in between the two. Now something that I'd like to note here, if your force is going one way and your direction is going the other, or your displacement is going the other, like if you're slowing an object down, you push against it, the angle between those two things is 180. And when you do cosine of 180, you get a -1. So you have an exactly negative work when you go in the opposite direction. You'll have a positive work in the maximum value if you do theta equals 0. If you do theta equals 0, that means you are pushing the exact same direction as your object is moving. So you're doing positive work in that case. And if you go at an angle, you're going to be doing some amount of work that is less than the maximum value you get when you do 0 or 180. But also, an interesting consequence of this is if you are pushing perpendicular to your object, that's the cosine of 90, you're going to end up with cosine of 90 is 0, so you're doing no work when you push perpendicular. And all of that just comes in from the idea of the dot product here in this work. Now you can also have a total work. So total work happens when you've got multiple things acting on an object. So for example, if you had a box sliding on rough ground, you would probably be pulling on it or pushing on it, Fa. You've also got gravity, and you've got normal force, and probably some force of friction if you're on the rough ground. So you've got lots of different forces doing work there. When you do that, you kind of really have two options, assuming they're all acting for the same period of time. You can either find the net force, so the net force here would be a vector. In the x direction, you've got Fa minus Ff, and in the y direction, you've got Fn minus Fg. Okay, so that's your force vector, and then you would dot that with your distance vector, whatever your distance in the I direction, distance in the j direction is. You do the dot product there. So you could go ahead and find the sum of forces and say the work total, or the work net, equals the net force dotted with the distance. Okay, or you can find the net work by adding up the work from each force. Work from applied plus work from friction plus work from normal plus work from gravity. Now, what you would notice maybe about this situation is your normal force and your gravity are probably going to cancel out because they're over here in this y component, and chances are your box is probably not moving in the y direction. So when you take the dot product, those would go away, which would be taken care of down here in this version, because when you do your FD cosine theta, if you were doing it that way, your angle between the distance moved, assuming you're moving horizontally, is going to be 90, and those are going to cancel and go away. So there's multiple ways to approach it when you're looking at multiple forces. You can either do component-wise, adding up all the forces beforehand and dotting that with your distance, or you can find all the works individually and add them up. Either way is going to work. I'm not going to do an example of that. I'm hoping you guys just understand the concept. If you don't, ask me some questions. But we're going to move on to the more advanced stuff. You guys know how to take a dot product, so that previous definition should be pretty easy. But forces do not always have to be constant, and your path does not always have to be straight. So the section 6.3 of the book deals with variant forces, or varying forces. And I'm also going to throw in a little bit about varying paths. So a more general definition of work is the integral from position 1 to position 2. So that's like if this is your path, position 1 is where you start, position 2 is where you end. Everything in between is your path. It's the integral of the force times dx. Now, this particular definition is a straight line. That is when your particle or your object is constrained to be moving. It can move back and forth, but it's moving just along the x-axis. It's not moving anywhere else through space. However, this can actually be generalized even further by rewriting it just a little bit. It's the same form, but we would have R1 and R2. Those are position 1 and position 2. They can have any number of dimensions, any number of coordinates, though we'll stick to the typical 3. And that's of the force dotted with dl, okay? And this is where L is the function of the path. L is function of path. And I'll explain what I mean by that later. So we've had 3 definitions of work. We've got work equals force dot distance, and then we've got the integral definitions, one for straight line, one for a non-straight line. So the idea here is that we're generalizing our concept of work. And when I mean generalizing is most of your physics knowledge has been for very specific cases. Like kinematics only work when your acceleration is constant. So if your acceleration isn't constant, that whole portion of physics is obsolete. It doesn't work. Okay, so what we're always striving for is a more general definition that works with more cases. So this first case, F dot D, that only works with constant force. But we're escalating to the second definition. It's more general because it works for a non-constant force, but it is constrained only for straight lines. And then the last one is completely general. You can have a varying force, you can have a varying path, so that could really apply to any situation beyond accounting for like relativity and quantum mechanics and that kind of stuff, which is way beyond the scope of us. So it's a really, really general definition, which means it's going to be the best definition. But what happens with really general things is they become hard to use because they have to take in so many cases, and they usually deal with a lot more complex math, which is why they don't teach them to you in the first place. So we're working from that limited definition and trying to move to a much more general one that works for a lot more cases. So now we're going to start looking in depth at the definition that is work equals the integral from position 1 to position 2 of fx dx, where the particle is constrained to go in a straight line, which means the force is also constrained to go only in the x direction. So when we do the dot product here, really this should be a dot product, fx dot dx, but if they're both only go in the x direction, so fx dot dx, and that's just the x direction. Really the dot product is just the two things multiplied together. Okay, so we don't have to really worry about the dot product because it is just the fx times the dx. So what a question would look like in this is you would have some function of x for the force. So your force is based on position equals something. Now, right now, we're going to look at the case for a spring, and we're going to do a derivation with that. Now, we haven't talked about it in this class. You might know it from UIL. You might have seen it before. But the force for a spring, how much force a spring creates or pulls on an object, whatever, it's based on how far it's stretched from its starting position, and that is based on the idea of x. So the force for a spring is written as negative kx, where k is a spring constant. It does not change with x. It is a constant, but it's based on, or the force is based on your x position. Now we're going to say, just to make things nice and easy, that where x is 0, that is where the spring is unstretched, so the equilibrium state for a spring. When the object is at 0, that's the equilibrium state for the spring. If we pull it any further than that, it's stretching the spring. If we push it any further towards the spring, it's compressing the spring. But where our object is at 0 is where the spring is at equilibrium. So if we take that function and we plug it into our integral, I'm actually going to make this stuff a little bit smaller real quick. If we plug that function into our integral, we get work done from a spring is the integral from the starting position to the ending position times fx, which is negative kx dx. And you would integrate that just like normal. You can pull the negative kx out, or sorry, the negative k out because it's a constant. So you've got negative k, integral from x is 1 to x is 2 of x dx. We all know the integral of x dx. So we get negative x, and this is x squared over 2 from x1 to x2. And then we got to plug in our arguments there. So you've got negative k times x2 squared over 2 minus x1 squared over 2, which can be even further simplified by saying it's negative k over 2 times x2 squared minus x1 squared. Same deal. So our work would be this, and you could then input, if you had actual starting and ending positions, you could input those as x2 and x1. So if you've got some kind of force equation, force function, you can plug that in here for your fx. So let's do a quick example problem with that one. So this example is example 6.6 out of the textbook, if you want to go refer to it there ever. It says a woman weighing 600 newtons steps on a bathroom scale that contains a stiff spring. In equilibrium, the spring is compressed 1 centimeter under her weight. Find the force constant of the spring and the total work done on it during the compression. Okay, so first things first is the force constant. Now this is going to harken back to our force days for a second. I just said the word harken. Lovely. We're going to need a little free body diagram here. It says that she's stepping on the scale, reaches equilibrium, and so the forces here are mass times gravity equals k times x. And this happens when x is compressed 1 centimeter. So if you said this was the negative kx, like it's technically defined, compressing it 1 centimeter makes it negative x there. So the negatives will end up canceling out. And you'll get your mass times gravity has to be equal to k times 0.01 centimeters. And the mass times the gravity is 600 newtons because that's the weight. So we've got 600 equals k times 0.01. So all you got to do is multiply both sides by 100, and you get k equals 60,000. And that's newtons divided by meters is the unit there, because this was newtons, that's meters. So that's kind of a trivial thing. Finding the spring constant deals with forces from a while back. But the question is, what's the total work done on it during the compression? This is work done on the spring. And then we get to do our lovely formula here. So we've got the integral. It's work equals the integral of negative kx, because that's our force function, dx. And we're going from the original 0, and it's getting compressed 1 centimeter, so that's going negative 0.01 really. And now we get to do that integral. Work equals negative k is negative 60,000. It's the same integral we just did. Integral from 0 to negative 0.01 of x dx, which is going to be negative 60,000 times x squared over 2, and that's evaluated from 0 to negative 0.01. And we get to plug all that stuff in. We'll go ahead and do negative 60,000 divided by 2. It's negative 30,000. And we've got x2 squared minus x1 squared. x2 is negative 0.01. So it's negative 0.01 squared minus 0 squared, which we should know is 0. So then we've got negative 30,000 times 0.01 squared, so 0.0001, or same thing as dividing by 100 twice, but times 0.0001 gives us negative 3 joules. So there you have it. Now there is a slight caveat to this that we'll discuss more next class, so I didn't really bring it in this time around because we're just learning how to do the integral. That we just found is actually the work done by the spring, not the work done on the spring. So those two things, work done by an object and work done on an object, are exactly opposite in sign. Same number, but opposite in sign. So if we really wanted to find the total work done on the spring, this is by the spring, we just flip the sign, and that makes it on the spring. So your book will say 3 joules, which is correct for having the work done on the thing. But we'll talk about that when we do work energy theorem, not now when we're just calculating work. The most general definition that we gave for work is that work equals the integral from position 1 to position 2 of, what did I say? Force dotted with dl, where L is path. Okay, now we're not going to do a whole question of this because there's not really a good one in here that we can mathematically handle. So I'll give you kind of an idea of what that looks like. So say we have a spring. Okay, we got a spring right here attached to some point, like so, and it's attached to a marble, and the marble's on a track, and the track is parabolic. So if we had to give this track a function, this is y equals x squared, and the marble can only follow that path. And the spring is going to be changing direction as the marble rolls. As the marble rolls up, the spring moves up with it. So that angle there is constantly going to be changing. So the direction of the force changes, the distance changing. The distance from there to there is much less than the distance from here to here. So as your marble rolls, your force is changing both in magnitude and in direction, and your path is also changing in direction. So there's a lot going on there, a lot of variables. So what you would have to do is write both of those things as functions. Now, the tricky part about this is coordinate systems, and we're just going to barely scratch the surface of coordinate systems here. There's two main two-dimensional coordinate systems, and we're only doing 2D stuff right here in this question. Okay, there's Cartesian that uses x and y, and then there's polar that uses theta and r, or usually it's r and theta. And these are not directly translated. Going 1x, 1y is not 1 theta, 1 r. Okay, the relationship is that x equals r times cosine of theta and y equals r times sine of theta. Okay, so in writing integrals that don't go in a straight line, a lot of times it's more convenient to use the r and theta coordinate system, the polar, rather than the Cartesian. So you would have to write your force as a function of one of those things, or one of those sets of things. Write your force either as a vector in x and y, or as in r and theta. We're going to keep it in x and y for now because I know you guys aren't very familiar with polar coordinates. So your force for a spring is negative kx, which is based on the amount that it is stretched or compressed. So you'd have to write your force function in terms of that, but where this x is actually the distance. So that's kind of like the square root of your x squared plus y squared. Now really there would be some offset because the distance is never going to be actually 0. The spring wouldn't be touching the track, so it'd be like x minus something and y plus or y minus something. I'm not going to deal with that right now because we're not actually solving this out, but this could be the general form of it. Okay, so that would be like your magnitude, and then your direction would always be changing. So the part of this that would be in the x direction is related to the part that would be in the y direction using some trig. Or you could also do it using ratios, because if we're doing trig, we would have to use angles, and we're trying not to use angles in our coordinate system here. So if this was our magnitude total, I'll indicate as right there, then the part of that that goes in the x direction is going to be proportionally related to that. So what it's going to end up being, and this is kind of wackadoo, a little bit crazy, I'm going to skip through a bunch of algebraic steps here, is your force would end up being a function that looks like negative k x, negative k y, because when you do Pythagorean theorem on that and get the magnitude, you're going to end up with the negative k times the square root of x squared plus y squared. Okay, so that would be your force function, kind of. Realistically, there would be a little bit of difference there, but that's something it could look similar to. So force function, not too bad. But your path function that you're using is going to be, oh, sorry, I just wrote force. The displacement could be written as x and y, or the path is written as x and y along the route, though. So when you do the x and y, if you're looking at your position vector at any point in time, it's given somewhere on x and y. If you look at this point, it's got an x and y. However, we are constrained to be on the x squared path. So instead of y, wherever there's a y, I can put an x squared. So we erase the y wherever it's at and put an x squared, because that's how those things are related as our situation is constrained. So when we did our force dot dl, we're going to be dotting those two things. However, this is just the displacement, or L as it's been written up there. We have to find the dl. So we'd have to take the derivative of this with respect to x, because that's the coordinate that we're using here. So the derivative of this with respect to x is going to be 1 and 2x dx for both of them. So when I would do the integral here, we're really going to be doing, sorry, I'm being really messy. This is where I'm going to be doing the work. The integral is from position 1 to position 2, so that's x1 to x2, because my y value is constrained to be relative to my x. I'm doing everything dx. It's going to be the dot product of negative kx squared dotted with 1, 2x. So then I could do the dot product of those and take the integral. So it'd be like negative kx plus negative 2x cubed. And then I would do the integral from x1 to x2 of that to get my work. So it'd be negative kx squared over 2 minus, oh, I forgot the k here, minus 1/2 kx to the 4th. And then you'd plug in your stuff. Anyway, so the point is, the very general definition is not constrained to be along a path, and that's kind of what it would look like. You guys don't have to be able to do that problem. I just think it's an interesting case and fun to be able to see what's possible. All right, I think that gives you like 6 questions to do of practice. None of them involve anything besides a straight line, so you should be good in that regard. But please let me know if you got questions or need any help. We'll be talking about how work and energy are related next class period.